Okay, so what I'm going to do is I'm going to integrate this both equation from 0 to delta. Okay, both equations. So let's do that on the uh, so du dx dy plus dv dy 0. Okay, now here I can integrate this. So I get v at delta means infinity minus v naught. So v naught is 0, you know, at the plate is going to be 0. So I get v infinity, I get a term to repeat v infinities minus 0 to delta of du dx dy. Okay, let's keep that. Okay, so let's just write it down on here, and then we erase everything there. So here v infinity is equal to minus du dx dy. Okay, let's keep that from the yeah. Any question? Hello, somebody had a question? Feel free. It's not a problem. Okay. All right. So let's just and I'm going to integrate the momentum equation now. It's a laborious process. This I can easily erase the uh, whole board, but I can't erase this writing. Okay, so let's integrate the first equation here. So I get everything has to be dy. Okay, so here, okay, so I get 0 to delta u du dx dy. So let's just take this one is equal to 0 to delta d over dy of uv minus u dv dy is equal to minus nu du dy y is 0. Because I can integrate the right hand side dy, and then this is how I get. So this I got. So let's just so dv dy. All right. So let's just do this. So dv dy is what here from the continuity equation. Dv dy is nothing but du dx minus du dx. So I can substitute du. I can multiply this. This is equal to du dx. Okay, so I get 2 du dx. I can take this one out, dy. Okay, now here, so I get this is nothing but 0 to delta d of dx of u square dy. So it's nothing but du dx is equal to vu. One is a delta or infinity minus this both are 0 is equal to u du dy. So this v infinity is what? So 0 to infinity, I'm sorry, du square dx dy plus u infinity. So v infinity we already showed earlier is nothing but minus 0 to delta du dx dy is equal to minus mu du dy y 0. Okay, so this u square is there. I can bring in u infinity See, du infinity is 0. So du infinity, I'm sorry, du minus u infinity multiplied by u. So they have already taken this into that here. So this can be taken out. So what do I get? I get, so I'm going to erase the whole thing. So I get 0 to delta d over dx u minus u infinity u dy is equal to minus nu du dy y 0. Okay, I change u to u infinity and bring the dx outside because the I can bring the because it is a function of x, it's not partial difference. I can bring the total difference because when you integrate out, you will only get a function of x. So I can bring the differentiation outside. So because of the negative sign, it becomes positive here. So that's it, QED. So we use the continuity momentum equation, continuity equation, and got this one. Similarly, remember the energy equation is what? U dt du v dt dy is alpha d square t over dy square. And I can integrate this again. So what you get? So integrate 0 to delta t, of course, u dt du dy. So this can be converted into, okay, 0 to delta t d vt over dy. This should be dx, I'm sorry, should be x. dy minus t dv dy. Because so this one vt at infinity, then again do dt. So here t infinity v infinity dv dy is nothing but dv dx. So this is nothing but dv dx is equal to this. Okay, so let's just do the let's see the other let me erase this one. Must be a better way to do this, but anyway, it's okay. Okay, so I'm going to take this equation. So basically what I have from the energy equation, same steps. So energy equation I have 0 to the thermal boundary layer delta T u dt dx dy. So dv dy is du dx. Okay, that's okay. Du dx. Okay, no problem. Yeah. Okay, so this plus vt v infinity t infinity minus that is 0 0 plus t. This is the problem there somewhere. Yeah, v infinity we already solved. What does v infinity was? T infinity minus of that 0 to delta t of du dx dy. Okay, so this Vt0, Vt dt du dx, what happened there? Oh, that's nothing but 2 du. Okay, so this nothing but becomes 0 to delta t d over dx t minus t infinity u dy. So is nothing but minus alpha dt over dy. So I can bring the t infinity here and t there and then take this plus. So then d over dx comes out outside. So that's it. So this, that is our equation. So from the governing equation, we can get the, without going through the fundamental derivation, you can get the integral equation just by first principle. So let me just, next page, I did the, yeah, this is straightforward. So this is the equation there. So u dt, so this is dvt minus t dv by dy. Remember that I showed you that. So dt dx, v d infinity u dt dx. So dv dy is nothing but minus ut dt dx. So I should have done that one. Okay, I'm not sure whether it's correct. Anyway, so this is, so basically I'm combining this and this as t infinity of u d over dx dy, and that is how I got this. So there is one more term here. This u infinity and u can be combined. In other words, this one and this one can be combined into one term here. So this one and this one can be combined in one term here. So the dut dA is nothing but this and this is combined, and then I bring the infinity here, becomes like this. So that's all. So it's just a slight manipulation of these terms to get the, finally this is the equation we got. So anyway, now we will, that is how, and basically once you make the assumption for anything, like for example in this case, let me just show some typical, you can I can assume some uh, some very approximate velocity profile, for example. So let's say the problem can be given. So I want to use this to be infinity or t infinity, doesn't matter. T infinity minus t so I can assume that u is, there hardly any, so u is u infinity. In other words, my velocity profile is not changing. So I can bring the u infinity here, and then I can assume maybe a cubic function there, and we can assume that t over t infinity could be some sort of simple function, maybe y over delta t alpha t whole cubed. Okay, so or whatever, so I can bring that one and then integrate it out. Similarly, on the right hand side, I substitute, and eventually I can solve for the h t infinity minus I'm sorry, t wall minus t infinity, or depending upon which is heating what, is equal to minus k dt dy at y is 0. So once I know the velocity, the temperature profile, I can from here I can really hd over k will be, or h some temperature, some formula, h over k will be my Nusselt's number based on the L or X or whatever. So that is how I get, once I, the temperature profile is known, x1. Then the velocity profile is known. Then I can get the Nusselt's number and then heat transfer and so on and so forth. So anyway, that is the idea here is you have been able to solve the approximate equation to get a very approximate solution to the problem, except the most important thing is it is indicating some non-dimensional parameters that you could potentially use to get the actual experimental results and empirically fit the data. So for actual conditions. So that is how the progress of heat transfer has occurred. A lot of empiricism, and because we got to be practical. I mean, Navier-Stokes equation is not easy to solve. So people have adapted this such approximate methodology to really solve and then do experiments. It could be time consuming and expensive, but that is how the science has progressed. So let me show some typical, I don't know whether you're able to see this one. Let me see. Are you able to see this very well?
Yes, sir.
No problem at all? Okay. All right. So this is some of the empirical relations of calculating friction factors and heat transfer coefficient on slightly curved or a flat plate. Okay. So basically less than 5 × 10⁵ means laminar. Okay, at any x. So it's basically 664. Remember the average local friction coefficient was divided by the Reynolds number. So we know that. Local Nusselt's number, there was a Prandtl number coming in. So Prandtl number was coming in. I'm not sure what the heck is going on. Come on there. Okay, so Prandtl number 1/3 is only 0.33. So that came in because it seems to fit a large percentage of Prandtl number. Okay, so it can be Nusselt's number can be two different ones. If it is Reynolds number is less than, this is laminar of course, but Prandtl number is greater than 0.5, you apply the top one. Less than 0.1, very small Prandtl number. In other words, the boundary layer is, thermal boundary layer is much higher than so it's like a liquid metal. In that case, you use the lower correlation. Whereas if it is the typical oil and stuff like that, you use the top. And average friction coefficient, again, laminar flow is 1.33 because this has to be integrated out. So we get averages again, Reynolds number based on the length of the plate. And then average Nusselt's number similarly, same thing, except that you see this is basically double this number basically. Okay, in the case of turbulent flow, which we haven't done this here, you can use the Reynolds analogy for turbulent flow, except the velocity profile is, they assume the 1/7 power law, but there are some issues with the boundary conditions, but they ignore that, and then they get some, theoretically you can evaluate using the Colburn Reynolds analogy, but the empiricism is basically what we have found out. Now the local Nusselt's number at a distance x on a plate which is turbulent flow, which is greater than 5 × 10⁵, and Prandtl number greater than 0.5, is this Nusselt's number is 0.0288, Reynolds number 1/3. Okay, this is the 0.8 comes in even for at the Reynolds number to the power of 0.8, even for a circular pipe flow, not only flat plate. So interesting. Turbulent flow, of course. In a pipe flow greater than 5,000 will be turbulent. Now, average friction coefficient, it becomes critical at a particular point xc, because remember at the initial point it may still be laminar, the boundary layer will get to the critical thickness and it will become turbulent. Once it reaches the critical Reynolds number, Reynolds number is changing as if x is changing. So at that particular x, at the critical distance x, then you need to have consider that particular point where it becomes turbulent. Okay. So the average friction coefficient given by that correlation, average Nusselt's number, again turbulent flow, Prandtl number greater than 0.5 is 0.036 Prandtl number. Okay, so this basically on a flat plate it reaches turbulence probably 23,200. I mean that's the reason this number has come over, some number here. Okay, so now if you want to calculate the average friction coefficient, it's the function of x 0 to L 1 over L integral. So that's how we do it, and all those average numbers are defined accordingly. Okay, so let's go to the next set of correlations. This is the same. I think I'm just a little bit more elaborate. You know, that again Prandtl number greater than 100. Remember there the Prandtl number was the earlier it was a little bit lower. Still laminar, but Prandtl number is higher than 100. So Prandtl number higher than 100 means the velocity, the boundary layer is much bigger than the thermal boundary layers. Typically for oil, it will be much bigger. So for oil, because the Prandtl number is high, the viscous dissipation cannot be ignored. In the integral equation, you cannot ignore the viscous dissipation. So you may have to consider that. So the Nusselt's number is given, and this is the correlation for that condition. Still laminar, and again Prandtl number less than 50. You know, between 0.6 and 50. Then here this is Reynolds number multiplied by Prandtl number greater than 100. That's what this is, not Prandtl number. So that's a product of that. Let's see. Now here, this is the difference between this and this is, here the temperature of the plate is constant. It's not getting heated, whereas this one it is getting heated. There's constant flux into the heat. So that's the correlation. Similarly, the second one is, for this particular case, this is the correlation. So anyway, to make the story short, very practical cases that you want to solve, they're all empirically solved, and they're all available on handbooks. And here that we just saw this for laminar flow, we just saw that that we derived this using the velocity profile and temperature profile. We knew that. And the next case is flat plate for turbulent flow. Basically, you use the Stanton number and the PR23. This is basically the Colburn analogy comes in here, and you can use this from the friction value, and you can solve the problem for the, because remember this is a function of the heat transfer coefficient divided by the velocity, free stream velocity, and multiplied by the density and Cp. I think I'm not so sure exactly how the Stanton number is. I got to check, but it's a non-dimensional number. Okay. Anyway, for turbulent flow, number of correlations are available on this page. So if you need to refer to it, you can refer to it here. Okay. All right. Let's see what next page. We'll do that tomorrow. So when we can have the YY, tomorrow is not convenient. Can we have it on a Saturday? I mean your Saturday?
Okay.
Krishna, you want to check on it? Let me know.
So most of them have said they're okay with any timing. Only one of them did have a problem with tonight.
Only one of them has. Who has a problem? Who has a problem?
He's not here today.
Okay. Okay.